Hello, students. We're back. Hope that Dr. Perot's videos were helpful in understanding how the procedures go. So what I want to do now is I want to discuss the first part of the experiment, which is the calibration of the calorimeter. So let's go to our pages here. Uh, if you go to your lab manual on page 36, they explain how the calibration goes here in the bottom. And don't forget, this is very dense text in here. And the expectation is that you will have read this and converted it into a step-by-step, easy to follow outline form, all right? But essentially the experiment consists of mixing a sample of cold water with a sample of warmer water, all right? So let's see how that works here. I'm gonna kind of put us here on a blank piece of paper here, and let's talk about that. So this is essentially the calibration of the calorimeter. And what we're going to do, as I was saying, and as the procedures describe, is you're going to have a sample of cold water. We're going to say that has a temperature T1, and a sample of, I'm just going to call it for the sake of illustration, warm water at a temperature T2, all right? And the idea is that when you combine them, right, it's the same substance. So therefore, the energy exchange is going to depend exclusively on what is the temperature difference between the two of them. And you would expect that because they are both the same substance and the same amount, your final temperature of this should be essentially the half point between the two temperatures. So it should be T1 plus T2 divided by 2. In reality, that is not the case. Typically, the actual final temperature that you arrive at is larger than what should be the midpoint between the cold and the warm water temperature. So why is that? Well, let's go ahead and look at our calorimeter, and let's kind of like zoom in on what's going on. I'm going to do just a sketch here. So let's pretend that this is the wall of the calorimeter. Please forgive me for my poor sketching skills here. Okay, this is the outside, which is pretty much air. And this is the inside, which is where the water is. Now, like I said, theoretically, the water, when you combine the warm and the cold water, should have arrived at a temperature that was essentially the half point between the cold and the warm temperature. But we end up with a different temperature than that. Why is that? The reason is that the calorimeter is not a perfect insulator. The calorimeter is having a temperature outside, which is the room temperature, which is higher than the supposed endpoint of the temperature of the water inside. Since this temperature on the outside is higher, there is going to be a net transfer of heat from the outside in, and that is what's going to cause for you to get a final temperature of the water inside the calorimeter that is slightly higher than the temperature it should have arrived at. So for example, let's say your cold water was at 5 degrees Celsius and your warm water was at 25. Well, you would expect when you combine equal amounts of them to land at a temperature halfway between them, 15 degrees. But when you actually measure it, it turns out to be maybe 16 and a half. And that's because the calorimeter, although it's an insulator, it's not perfect. And so it does allow a little bit of heat exchange. And that's what we're trying to measure. what is the calorimeter responsible for during any energy transaction that happens inside when you are doing a regular chemical reaction. Okay, once more, let's remember, according to the law of conservation of energy, that the total heat in here should be the heat that is exchanged by the water itself plus the heat exchanged by the calorimeter, and that should total to 0 according to the law of conservation of energy, right? That should be it. So let's rearrange this equation and find out that the heat exchange for the calorimeter would be minus the heat exchange for the water. Now, here's very important. This heat exchange of the water is not between the warm and the cold water. It doesn't refer to that, okay? It's very important you understand that. This is not the energy exchange that happens when you mix the cold and the warm water. That's not what this energy exchange is for. This is for the energy change that caused, this is what caused the final temperature to be larger or higher than the midpoint between the cold and the warm temperatures, all right? In other words, what was the nature of this heat exchange that made this temperature actually land at a bit of a higher value? Now let's see what these things are. Okay, for the calorimeter, you would have the heat capacity of the calorimeter times the temperature change. Now the calorimeter started at room temperature and ended up at T final. So the temperature change that we're talking about here is the difference between the final temperature and the room temperature. And of course, this is in degrees Celsius here. For the water, we would have what is the mass of water times the specific heat of water, which is a constant that we can find, times the temperature change for the water. Now, what is that temperature change for the water? Remember, it's not between the cold and warm water. It's between what the water should have landed at and where it ended up finishing in terms of temperature. So that would be the final temperature minus what the temperature actually should have been. Okay, that's what we're looking for. Now, what we're going to do in our experiment is we're going to have a way of measuring what the final temperature is. We know what the initial and final temperatures are. We can measure what the room temperature is. We can calculate the mass of water. The specific heat of water is a constant, and therefore what that means is that mathematically we can simply use these values and algebra to calculate what is the heat capacity of our calorimeter. Okay, so in the first part of the experiment, you will perform 3 trials of this exchange between cold and warmer water, and you would essentially mix them in the calorimeter and measure the temperature every 30 seconds for a few minutes, as Dr. Perot illustrated in her video. All right, now in our case, you will be receiving a data sheet that has all the information filled in, and you can either copy it to your own blank data sheet, or you can use the one that you're going to receive and just submit that. Doesn't matter. But our goal is to find out what was the actual final temperature that the water arrived at when you mix the cold and the warm water. That has to be done from a graph, because even though sometimes the temperature here stays constant, it kind of fluctuates a bit, and it might be hard visually to identify what was that final temperature. So let's go ahead and switch over here. We are going to go back to our screen over here, and let's talk about this for a moment here. All right. So in here, what I've done is on an Excel spreadsheet, I have copied the data from a sample data set. This is not the same one that you're going to get, okay? Yours is going to be different. So be aware of that, okay? Notice that we have here the time in half-minute increments, and then the temperatures for trial 1, trial 2, trial 3. I'm going to focus here on trial number 1. All right, we're going to look at what was the profile of those temperatures. Notice that we have here the room temperature, we have the temperature of the cold water, and we have the temperature of the tap water, which is what I'm calling the warm water. So if you do a plot of the temperature versus the time, Excel might do something like this. Notice that because Excel essentially concentrated all of the display in the span or range of about ½ degree Celsius, the data points look pretty scattered, which gives a wrong perspective. It gives the wrong impression that there's a lot of variation here. So what you need to do is you need to bring this to realistic levels. In other words, we are looking at ranges of temperature in today's experiment between 0 and like 40 degrees or something like that. So it'd probably be better to kind of like represent on the graph the ranges of temperatures we're talking about. If you forgot how to do it, please go back to our graphing exercise of week 1, or use the help menu in your Excel software or whatever graphing software you're using, so that you can come in here and essentially change the temperature axis to a more manageable, more realistic range. And that's what I've done in the next slide, in the next graph. See, this is more realistic in terms of the span of temperatures. If the cold water was at 7 and room temperature was 20, it makes more sense to have a range of temperatures like that in the graph. And now it highlights how straight the line looks at here. So I'm going to have Excel do a trend line and give me an equation of the line, because it allows me to project that line all the way back here to the y-axis, where I can read what was that final temperature, what seems to be the temperature this settled around, and that gives me what the final temperature is for this first experiment, which is 13.5. You can see it there. Now, if you repeat the graphing and the calculations with the other two trials, you find, again, each one of them has a different final temperature. So the question now is, what are we going to do with this data? All right, so I'm going to bring this over here to a graph for the calibration and put this on a piece of paper here. So let me come back out here, and let's go back to our makeshift whiteboard here. So let me see if I can zoom in a little bit in here so you can see it a little better. Let's see if we can, like I said, zoom in a little bit. There you go. Okay, so what we said was that after looking at the reaction here, we saw that there was, although you can barely see it here, the final temperature here we landed at was 13.5 degrees Celsius. All right. Now let's look at our calculations. Now, we said that in this process, the total heat exchange for the calorimeter is minus the heat exchange for the water, right? They exchange energy between each other. For the calorimeter, that would be the heat capacity of the calorimeter times the temperature change in the calorimeter. For water, it would be, again, minus the mass of water times the specific heat of the water times the temperature change that the water experienced. Don't forget, we're talking about the change between what the water should have ended at, which is the half point between the cold and warm waters, and the actual final temperature that it arrived at. Let's rearrange this equation to solve for our unknown, which is the heat capacity of the calorimeter. So that would be minus M of water times C of water times delta T of the water divided by the delta T of the calorimeter. Now remember what we said about these quantities here. What is the actual temperature change we're talking about for the water? All right. Well, we're saying that this is the difference between the actual final temperature and what that temperature should have been in an ideal situation. In other words, half point between the cold and warm water. For the calorimeter, we're talking about the exchange that happened because the temperature that the calorimeter ends at is lower than the temperature that the calorimeter started at, which was the room temperature. All right. So I'm going to go ahead and put all these numbers in here and see if we can have enough room here. All right. I'm going to try to make enough room here for all of this. Okay, here we go. So we don't know what the mass of water is, but we know that we added 100 milliliters total because there was 50.0 of cold water and 50.0 of warm water. And water at this stage has a density of about 1 gram per milliliter. So that cancels the milliliters out and gives us grams. The specific heat of water is a constant. It's 4.184 joules per gram per degree Celsius. So that knocks out the grams. And the temperature change would have been the final, which was 13.5 minus the actual midpoint between the cold and the warm temperature, 7.2 plus 19.0. I have these numbers up here. You can check back in the video when I show you the slide. You can see it a little bigger there, divided by 2. And run out of space here. So this is degrees Celsius, which means those are going to cancel out here. All right. All of that is going to be divided by the temperature change of the calorimeter, which would be the final temperature, again, 13.5, minus room temperature, which in this experiment was 20.0 degrees Celsius. Notice that because this number here is going to be negative, it's going to cause that negative to cancel out also. These degrees Celsius are not going to cancel out because the units of the heat capacity are joules per degree Celsius. That's the amount of energy to increase the calorimeter's temperature by 1 degree Celsius. I'm not going to do all the math here, but I'm going to tell you that this is going to land at 25.7 joules per degree Celsius. Okay? Now, what you're going to do is you're going to be doing 3 trials, right? So for each of the trials for which you have data in your data sheet, you're going to be calculating from a graph what is the final temperature and therefore what would be the heat capacity of the calorimeter for each trial. All right. So coming back here, let's go to our screen again. Let's look at our graphics again. So what I did here was I calculated the heat capacity of the calorimeter for all 3 trials. All right. And that's going to be 25.7 is the one we just did, 19.8, 22.2. And then I'm going to get the average of all 3 of them down here, 22.6. So keep that number in mind because we're going to use it in the next set of calculations, okay? One of the typical errors that happen here is that you end up with a value of the heat capacity that is negative. And that's probably usually because you didn't stir the solution, the water well enough, and the temperature didn't distribute as well, and you ended up with a negative instead of a positive difference between the final temperature and what should have been the half point between the 2 temperatures of water. In that case, what you do is you drop that value. You don't include it into the averages. You only calculate the average of positive calculated values of the heat capacity of the calorimeter. Okay, so we got that now. And what I want you to do now is go ahead and take your data sheet that you received and go ahead and do these calculations and see if you can work on your graphs and see what comes up and calculate the average of all the 3 trials for the heat capacity of the calorimeter. Okay, I'll give you time to do that, and then we'll come back in the next video to talk about what happens with the actual chemical reaction. So I'll see you soon.